Today we're going to go and do a quick podcast on half-life, the time it takes for half a radioactive sample to decay. And if you recall, radiation is given off by different elements because they're not stable. Their protons and neutrons aren't equal or the ratio is off, and we'll go into that today a little bit. And first of all, if I say the word radiation, it is not a bad thing. As a matter of fact, if you look, many types of radiation are useful. There's radio waves, microwaves, infrared. And as you glance at this chart, you can look and see there's actually a temperature difference right here that's given off by objects where the radiation is emitted or given off. So if you have radio waves in this area, they have a very low temperature. And if you have gamma radiation on this side, it's very, very high temperature. And gamma radiation, as a matter of fact, comes from outer space, and that's what our ozone layer is protecting us from. Now there's also two other parts to this, which we'll come back to in another unit. There's wavelength, and there's frequency. Frequency is how often something happens, and if you'll notice on this end where radio waves are, it doesn't happen as frequently. They come very slowly. If you come over here where gamma rays are, the waves happen very often, and so the frequency increases. Very often. Very not often. Very slow. Now, if you look at wavelength, wavelength is the distance between two different crests on a wave. And so this is a crest, on top of a wave, and this is a crest. Look at the wavelength on this side. It's longer. And as you come over here, the wavelength is shorter. That's because they're coming more often. Again, we'll come back to this later. I just wanted you to be aware that there's different types of radiation. And if you look where visible light is, it's a very small part. And that's that Roy G. Biv. Those colors. So if I say radiation, don't run for the hills. It's not dangerous. Unless you have certain types. Now, alpha radiation, if you recall, is 4,2 helium. And that's symbolized with an alpha. And if you'll notice here, this is type 1, and it's stopped by your skin. We discussed that in class. Beta radiation number 2, right here, is stopped by aluminum, okay, or very thin wood, and beta radiation is 0 minus 1 electrons. That's a beta particle. Gamma or X-rays, they're not both the same thing, but gamma and X-rays are stopped by lead. That's why you use that at the dentist's office or the doctor's office. And so gamma radiation is a funny little symbol with a 0, 0, and we'll come back to that later. Okay, this is a form of energy. Whereas 1 and 2, alpha and beta, and this was beta right here, I ran out of room up there, those are actually particles. Now, neutrons are not radiation, but they're often formed with radiation, and they are stopped by concrete, very thick concrete. So the three types of radiation are alpha, 4,2 helium, beta, 0 minus 1 electron, and this is a helium nucleus, this is a fast-moving electron, and then gamma radiation, which is a form of energy, and we'll come back to that later. Just so you know, there's a reason why radiation is given off. And if you look, this is Z, the atomic number, the protons, and this is the atomic mass dealing with specifically just the neutrons. So if you look at the neutron-proton ratio, if they're a 1-to-1 ratio, that's this red line right here, which I'll now turn blue. That's a 1-to-1 ratio. The band of stability that exists with a ratio is in this area. So if you have a neutron to proton ratio, then that's where the atoms are stable. If they're on this side, they're not stable. If they're on this side, they're not stable. So to become stable, if you have too many neutrons, then you have beta decay. If you have too many protons, you have positron emission or electron capture. So I'm not expecting you repeat this to me, but that's so you can understand. And I'll show you a closer zoomed in graph here. These black dots on here are stable. So if you look, they're stable on this graph chart. If you look at the blue lines, these are beta emitters. Okay, so if there's way more neutrons than there are protons, see right here, here's your number of protons, here's your number of neutrons, way more neutrons than there are protons, so this is not even 60, and this is 85. This is where the betas are, 0 minus 1e, 0 minus 1e. So you can see there's this whole range in here where beta is given off. If I'm an alpha emitter, that's 4,2 helium, right? That's because I have more protons than I do neutrons, but that's only for specific elements. Mostly what happens is electron capture, where a nucleus of an atom actually catches one of its electrons, or it emits a positron, which is a 0 plus 1, a positive electron, and you can see that's in this whole area where I have protons and neutrons in this ratio. Not for something for you to understand necessarily or repeat, but just so you can see that there's times when beta particles are given off. And if you look again, there's way more neutrons, see this right here, than there are protons. That's when you give a beta particle off. Okay, if I give off an alpha particle, it's because I have way more protons than I do neutrons in certain cases. That's alpha. And electron capture or positron emission is in this area. Just so you can see, okay, because I know some of you are asking why. Why does it happen? And this red line right here is when the nucleus is stable. So if you have a 40 to 44 ratio, then you're stable. If you have a 60 to 80 ratio, then you're stable. If you fall on either side of it, you give off beta electron capture. If you're way over here, then you give off alpha particles. So let's get to the meat of this. Oh, and by the way, real quick, because we were looking at this before, this shows you that there's ionizing radiation. That's radiation that's not that good for you. X-rays, gamma rays, it damages your DNA, and certain types of ultraviolet. Whereas non-ionizing radiation is in this area, radio waves, microwaves, okay? And again, we'll come back to this further. But we're focusing on alpha, beta, and gamma for this. So let's look. We have transmutations. Radiation changes things. So if you look right here, I have potassium, 42 over 19, because I can look that up in the periodic table. And if you look, this is a beta particle. Beta radiation is given off. And I know that this is decay because I have potassium right here, and it's decaying. It's giving off a beta particle. It's also giving off something else. Okay, or actually what's happening is something's left behind. So if I have potassium and a beta particle is given off, both sides of my equation have to balance. So if I have, let me get rid of this here. If I have 42 where potassium is on the top, where the atomic mass is, then 42 needs to be over here as well. Because this side of the equation has to match this side. The reactants have to match the products. So, if you look, the 42 equals 42 plus 0, doesn't it? 42 on this side equals 0 plus 42. Now what about this side over here? 19. And I have a minus 1 on this side. What should I put in this blank? Well, what plus minus 1 equals 19? 20, right? And if you look on the periodic table, in 20's box is calcium. And so this transmutation, or beta decay, happens when 42 over 19 potassium gives off a beta particle, leaving behind 42 with a 20 for calcium. In this transmutation, this is alpha decay. Why is it decay? Because alpha radiation is given off. It's emitted. It's a product. It's produced. It's decay. Those all mean the same thing. And so if you look on the periodic table, in Pu's box, it's 94. So over here it's going to be 92 on the bottom, which means right away this is uranium. If I look at my top numbers, 4 plus what gives me 239? That's 235. If I look in uranium's box, this mass number does not match what's in the box, so it's called an isotope. If I look in calcium's box, this number doesn't match what's in the box, so this is also an isotope. So this is how isotopes are made. So again, these are both transmutations. They're both decay. And now what we're going to take a peek at is actually what's going on behind the scenes in this reaction. Oh, and by the way, here, there's all kinds of decays that can occur. So if you look, this is a decay chain for bismuth 212. All right, and what happens? Yikes, this looks complicated, doesn't it? Well, you start with uranium and it gives off an alpha particle. What's that? 4,2 helium. It takes 69 years for that to happen. Thorium is produced. And what happens after 1.9 years and an alpha particle is given off? Radium is produced. After 3.6 days, 4.2 helium is given off, right? That's an alpha particle, and radon is produced. So you can see as you go along this chain of decay, more and more daughters, these are all daughters, are produced. Lots of alpha radiations going on, and actually here's a beta. So when you look at a reaction like this, these reactions are just part of a huge process. And so if you look, I started talking about this takes 69 days. This takes 1.9 years. So this is a chart that shows the different half-lives, we'll talk about that in a second, of these different elements and the type of radiation that's given off. Uranium-238 always gives off alpha radiation, and it takes 4.47 billion years for it to decay. It happens slowly over this time, but after 4.47 billion years, half of that sample is gone. We'll talk about that half-life in a minute. Lead-214 always gives off beta, and it takes 26.8 minutes for a total sample of lead to cut in half, which is called its half-life. So here we go. What is half-life? I have original sample, and the amount of time it takes for half of it to decay, where half of it is something else, and half of it is the original, and some type of radiation is given off. That is called half-life. Now from the outside, this sample does not look any different, but on the inside, half of it's potassium, let's say, and half of it's something new, calcium, and in this case, beta is given off. How does this happen? Well, if you look, cosmic radiation coming from outer space hits the Earth's atmosphere, collides with an atom, and creates a neutron. That neutron hits a nitrogen-14, and a proton goes flying off in space. That neutron gets captured by a carbon-14 atom, and the plants absorb carbon dioxide with a carbon-14. That's an isotope, because carbon is 12. And they absorb it through photosynthesis. Well, who eats plants? Animals and people. And so we take in carbon-14. Now, eventually, this poor horse is going to die. And what will happen is, after he dies and he gets buried, or if a tree dies and there's wood that's produced, the wood and the bones release carbon-14. When you and I are alive, there's a certain ratio of carbon-12 and carbon-14. Those are the two common isotopes. There's a ratio, it's a known ratio, of things that are alive. As something dies, carbon-14 is no longer taken in, and all the carbon-14 decays, giving off beta radiation, and nitrogen-14 is produced. And look, it goes back into the cycle again. So what we're going to look at is perhaps this carbon-14. And what we can look at is they can look and see what the ratio is. And if no more carbon-14 is being taken in, the carbon-14 amount goes down, and the carbon-12 stays the same. And so I can actually tell how old something is up to 60,000 years based on the carbon-12, carbon-14 ratio. We'll talk more about that in class, but this is one way half-life is used. So if you can see, if I have 100% all of an isotope, after one half-life, 50% of it remains, because one half-life means 50% goes away. So if I have all my sample here, this is 100 grams, and I tear it in half of it's something new, it gives off radiation, let's say a beta particle, and half of it's the original, so only 50 grams is left. After two half-lives, 25, 1/4 is left. After three half-lives, 12.5 grams is left. It's like a piece of paper that keeps tearing in half. You have 100% to start with, then you have 50%, then you have 25. So that's what half-life is. Again, it doesn't look any different from the outside. And you say, where do we use half-life? Well, we use it perhaps in nuclear medicine when you go to the hospital. They would inject you with a dose of medication. There's always a time 0, and there's always a starting amount, let's say 100 grams. Time goes by, let's say the half-life is 10 seconds. So after 10 seconds, 50 grams is left. If 10 more seconds goes by, that's a total of 20 seconds, but that half-life takes 10 seconds, 25 grams is left. So this is the amount. So you're always going to have time and amount. And we talk about time as t. Half-life, right here, is t 1/2. This is m sub 0, the original mass, and this is m sub t, the mass at a certain time. So let's do some problems. After 28 days, how much of a 200-gram sample of whatever, and it doesn't matter what's in this blank, that's going to change, don't let that bother you, is left? The half-life is 7 days. It doesn't matter which side of this box that you use, if you like to use this box strategy. You can always put time on one side and mass on the other. But time, original, is always going to be here, and it's always going to be 0. The original mass is going to go here, and the mass at time t is going to go here. Okay, and this is time t. So what do we know? After 28 days, so how much time has gone by? 28 days has gone by. So that goes down here. And it's days. How much of a 200-gram sample? Well, this is my original mass original, so I have 200 grams up here. And they want to know how much is left. So this is your question mark. The half-life is 7 days. So t 1/2 equals 7 days. So what do you know? You know that it takes 7 days to tear the sample in half. So this is 7 days. I'm going to put a D for days, okay? If that does happen after 7 days, how much do I have? I have 100 grams left. Have I reached 28 days yet? No. So I'm going to go ahead and have 7 more days pass. That's 14 days. How much is left? 50 grams. Have I reached 28 days yet? Nope. So I'm going to cut it in half again. 7 more days go by. That's a total of 21 days. How much is left? 25 grams. I'm still not at 28 days. As a matter of fact, I need to go one more, and now I'm at 28, right? Just the 7 and 7 and 7 and 7. So how much is left? 12.5 grams. That's how much is left. So my mass at time t is 12.5 grams. Now that's a long way to do it. Let me show you a shorter way. I have 2 times. I have 28 days. That's the total time, right? That's time. And I have t 1/2. My half-life is 7 days. If I ever have both those times, I can say to myself, 28 days total went by, right? And I always start at time 0. And my half-life is 7 days. So how many days or how many half-lives happened in those 28 days? So I can take 28 days and divide it by 7 days. Whenever you have 2 times, you can always divide the half-life into the total time. That gives me 4. That means this event happened 4 times. So what's my total mass at time 0? It's 200 grams. So I start with 200 grams. And so there's another strategy you can use instead of this box tearing in half. And I have 200 grams. So one half-life goes by and I have 100 grams left. Another half-life goes by, I have, 50 grams left. Sorry, I'm standing right in the shadow of the board as I'm writing. 50 grams left. Well, how many half-lives have passed? 1, 2, and I have a total of 4 I need to do. So I'm going to go ahead and go down like this. Sorry, I have 25 grams. That's half-life number 3, isn't it? And if you look now, half-life number 4, and if I planned this better I could continue off the board, sorry, or continue in a straight line, but I didn't do that, so I'm sorry. So if you look at this right here, what do I have left? 12.5 grams. So there's a different strategy for you. Let's go over here. I have 1,000 grams, and it doesn't matter what it is. It can be technetium, it can be uranium, it can be nitrogen-14. It doesn't matter what it is in this blank. It could be gold. It doesn't matter. You have 1,000 grams of whatever, decaying to 125 grams in 33.3 seconds. What is the half-life? Now be careful. You have 2 information pieces here, but they are not times. You can only take one time and divide it into another time. You cannot divide masses. So, what do I have? I have an original mass of 1, you know what, let's keep the times on the same side for you guys. So, I have 1,000 grams to start with, and it's a time 0. Okay? I know my total time here, right? My total time is 33.3 seconds. I start with 1,000 grams and I end up with 125 grams. So this is my mass at time 0, this is my mass at time t, and this is my t over here, time, the total time. What do they want to know? They want to know what the half-life is. Well, in this type of problem, you know that 1,000 grams is going to decay. What's it going to decay to? 500 grams? And that's one half-life. That's going to decay again to 250 grams. That's another half-life. And that's going to decay again to 125. How many total half-lives went by? If you look, I have 1, 2, 3 half-lives. That means in 33.3 seconds, this 1,000 grams split in half 3 times. So I take 33.3 and divide it by 3, and I get 11.1 seconds. And that's how long a half-life is. So this total time took 11.1 seconds, and that's the half-life. Let's go and do another problem. Now in this kind of problem, let's go back real quick. In the first problem, what do you know? You have time and you have half-life. So with total time and half-life, and you know how much of a original mass of a sample is left. So you know 28 days, you know the half-life is 7, you know the original mass, and you're trying to figure this out down here. That's one kind of problem. This is time is 0. Another kind of problem is you know the original mass, right? You know the ending mass, mass at time t, mass at time 0. You know the overall time, and you don't know the half-life. There's that kind of problem. The third kind of problem is this one. If I have 10 grams left, that's about 10, sorry. If I have 10 grams left, And my microphone just fell off. There we go. Of I don't care what it is, doesn't matter. After 40 days, so 40 days go by. Oh, I'm sorry. Let me go back. Okay, I'm going to try. I keep forgetting. It will help you if I keep things on the same side. So I have 40 days right here. It doesn't matter what side you put it on, but for you learning right now, time is over here and always is time 0, right? And what do I have? I have 10 grams left. See, so again, it does not matter which side you put it on, but I'm just trying to do it so I stay consistent so you can learn. 10 grams is left after 40 days. How much was in the original sample? And the half-life is 8 days. So you're trying to find out right here, mass at time 0. You know mass at time t, and you know t, total time, and you know t 1/2, the half-life. Oh look, what do you have? You have 2 times, 8 days and 40 days. So 40 total days went by, and every 8 days, this sample split in half. How many times is that? This event happened 5 times. So that means that 10 grams is left after this original sample cut in half 1, 2, 3, 4, 5 times. So if it's divided in half going in this direction, if you go back this way, you have to double it. So I'm going to take 10 grams times 2 times 2 times 2. When do I stop? At 5 times 2 times 2. So what would that be? 10 times 2 is 20 grams, times 2 is 40 grams, times 2 is 80 grams, times 2 is 160 grams, times 2 is 320 grams. So does everyone understand that if I cut it in half going in this direction, to figure out what I had originally, you've got to double it going in this direction. So in this direction, you divide it in half, you tear it in half. In this direction, you put the pieces back together, you multiply it by 2. How do you determine how many times? 8 into 40 goes 5. So I did 1, 2, 3, 4, 5 times. Now what if you don't have a word problem and you just have problems like this? Come on. Sorry. All right, I'll just start doing this right here. So what do I have? I have my original mass is 64 grams, right? And I have my half-life is, or I don't even have a half-life, do I? No half-life. Do I need it? Well, what are they telling me? I have 64 grams and it cut in half 4 times. So that means 64 turned into 32. That's 1 half-life. Turned into 16. Turned into 8. Turned into 4. That's 1 half-life, 2 half-lives, 3 half-lives, 4 half-lives, right here. And what do they want to know? They want to know the mass at time t, the final time, in grams. So that's 4 grams. All right, what do they give me information here? Do I know the final mass? No, I don't. I know the original mass. The original mass is 32 grams. Let's look at the other information they give me. They give me the total time is 8 years, and the half-life is 2. That means if you want to use my box method, that I don't know my original, I don't know this right here. So I know I have 32 grams. I know that 8 years total went by. I know that half-life is 2 years. So the time it takes to tear 32 grams in half is 2 years. So when 2 years go by, how much do I have left? 16 grams. I need to make it so that I don't have 2 years, I need to get to 8. So what did we say before? We said that if you have 2 times, I have 8 years, and I have 2 years, I can divide that 8 by the 2 and I get 4 different times. So that means that this is going to split in half 4 times. So I'm going to go ahead and do that right now, and then I'll show you the strategy with the box. So that's 4, and that's 2. And really what I'm doing here is the same thing as I'm doing with my box. I have 32 grams. It takes 2 years for it to cut in half, which would mean I have 16. It takes 2 more years. That means 4 total years have gone by. I'm not at 8 yet. And I have 8 grams left. So if I cut this in half again, I have 8 grams left. 2 half-lives, a total of 4 years. 2 more years go by. That's 6 years. I have 4 grams left. So if I cut this in half again, I have 4 grams left. That's a total of 2, 4, 6 years. I'm not at 8 years yet. So when 2 more years go by, I have a total of 2 grams left at the end. So if I went back to my box again, I would cut this in half. 1, 2, 3, 4 times. 32 to 16 divided by 2. Divided by 2 is 8. Divided by 2 is 4. Divided by 2 is 2 grams. Let's look at this last one. What are they saying here? They are saying that I have a mass at time t, sorry I didn't write that in, and I want to know mass at time 0. So what do I know? I know I'm left with 1 gram. I know my half-life is 10 minutes, the time it takes to tear it in half, and my total time is 40 minutes. So that means 40 total minutes went by, and each half-life took 10 minutes. That means 4 total half-lives went by. So what's that mean? If I have 1 gram at the end, right, this is my ending mass, how much originally was left. So I can look at my box if you want to. That means my mass here is 1 gram. I want to know what my original is. I don't know that. 40 minutes have gone by, and each half-life is 10. So this happened 1, 2, 3, 4 times, which means I'm going to double this 1, 2, 3, 4 times. Times 2, times 2, times 2, times 2. Because 40 minutes happened, and every 10 minutes they cut in half, so you have 4 total half-lives. So let me get rid of this mess here. Okay. So if I have 1 gram left, if you want to, you can even put it over here and work backwards. If I double that, I have 2 grams. That's 1 half-life. If I double it, I have 4 grams. If I double it, I have 8 grams. And if I double that, I have 16 grams. So you could do it backwards and have it make sense as well. My original mass is 16, and if 40 minutes went by, and every 10 minutes cut in half, that means that would be 1 half-life, 2 half-lives, 3 half-lives, 4 half-lives. 10, 10, 10, 10. And so indeed that works out, doesn't it? So remember, if you have a final mass and you want to find the original mass, then you need to work backwards and double it, put it back together. Good luck. Try and work on your worksheets.